Good morning. How's everybody doing? Welcome, thank you for coming. Very last day of AWS reInvent. I hope you guys have had a great week. Hope you have learned a lot this week. And I also hope that you've had a little bit of fun too, because after all, this is Vegas. Maybe some of you are kind of recovering from last night's party. I see a lot of suitcases, which makes me very sad because tonight is Friday night in Vegas. But hopefully you've had a great time. How many of you have the certainty that your service, your site, is ready to handle 3 to 4 times the amount of traffic that it's receiving right now? A few. Not that many. So here's you. You're having great dreams in your new satin sheets, and they're warm and comfy, and it's 4 o'clock in the morning, and unknown to you, surprise, maybe an influential blogger has posted a link to your site, or somehow it's gone viral. This is your big break. Lots of people are just flocking to your site. Will your site be able to handle what it's about to get? It's kind of like rolling the dice unless you've done the proper amount of load and performance testing. And us being in Vegas, maybe some of you have done a little bit of rolling the dice in the past few days. And if you did, you learned that sometimes you win, sometimes you don't, right? Here's the things that I want you to get out of the next 45 minutes or so. First one is that load and performance issues cost. They cost you a lot of money, they cost you customers, and they cost you reputation. These are a big deal to us at Amazon. Second part of this is not every load-related issue can be solved by adding more hardware. In the age of cloud computing, we tend to think that we just have infinite resources at our disposal, and we can do anything we want, and we can just add hardware to problems. That's not always the case. And even if you could, doesn't mean you should. We don't want you to throw your money away. But with proper load testing, you can identify the issues and you can prevent them, and you can fix them before they even show up, or at the very least, you can have a better idea of when they will happen and how to mitigate them. And last but not least, this is an AWS conference. So how did we use AWS? How do we use AWS in the retail site to do load and performance testing? In other words, we have systems that simulate the load that millions of users are putting onto the Amazon.com retail site. This is not an easy problem, but we solved it with AWS, and I'll be spending a little bit of time talking about how we did it and how you can too. A little bit about me. My name is Carlos-Arguelles. I'm a senior software engineer at Amazon. I've been at Amazon for about 5 years, and before that, I spent about 12 at Microsoft. Most of my professional career, I've worked with different teams in both of these companies doing load testing, performance, stress, and resilience testing. Currently, I'm working as the lead for and test architect for a number of test tools across the company, across Amazon. This is a very fun position because at Amazon, we have this amazing scale, and our load test tools have to do pretty much what our real users do. Like you, I am an AWS user. I'm not part of the AWS team. I started off in my Amazon career actually as part of the AWS team. I worked in Elastic load balancing and CloudWatch and auto-scaling and so forth. But I've spent the last few years in the retail site. So this is the Amazon.com retail site that you buy your lawnmower and your big screen TV and your toothbrush from. So we're a very, very big user of AWS. But this entire talk is not from the point of view of an AWS member, but rather as an AWS user. So let's talk about the Amazon.com retail site. First of all, we receive a lot of traffic. If you guys went to the session that Jason Hamilton, one of our senior distinguished engineers, did yesterday, he talked about scale a lot and the tremendous scale that we have to deal with in every aspect of our Amazon life. Amazon.com receives a lot of traffic. You can look at rankings. Usually we're in the top 5 in the nation, top 10 or so in the world. And creating systems that can handle this kind of load and creating systems that test those systems is quite a challenge. Just to be clear, there's no such thing as an Amazon.com app, right? When you go to Amazon.com, the front end is actually making many, many requests to hundreds of services under the hood. Every one of these services has to be scaled with a retail site. We have additional problems. We have significant fluctuation throughout the day. In this graph, each one of these little bumps is a day of traffic. In the red rectangle, that's 1 day of traffic. And you can see people don't buy a lot of stuff when they're sleeping. They wake up, they buy a bunch of stuff, they take a little break from shopping, and they buy a lot more, and then they go to sleep. So all our systems have to be designed to handle this huge fluctuation between day and night. It is tremendous. Additionally, not only do we have this big day and night fluctuation, we also have very, very different days. For example, what do we do after we finish eating our turkey on Thanksgiving? We go to Amazon.com to see what is the new big deal coming for Thanksgiving and for Black Friday and for Cyber Monday. So these 2 peaks here are Black Friday and Cyber Monday. They're very, very big deal for us. Some of our services get 2, 3, 4 times the amount of traffic, depending on how they're scaling and what they're actually doing. And this is a very, very high stakes day. We make a lot of money these days, and we want to make sure that when you go to Amazon.com after you finish your turkey meal, we will be up and running for you. And last but not least, we have significant growth year to year. Every year, a lot of our systems double or triple in traffic, and we don't want to be redesigning and rewriting systems every single year just because our load increases. So we have to think ahead and build things that will scale for years to come. Throughout my Amazon life, I've had the pleasure of breaking a lot of systems. What I do is I go into a team and I pretend to be friends with them, and then I break their system. And they don't like me so much anymore. But that makes for a few very interesting anecdotes about things that I ran into and load-related issues that I've discovered and so forth. There's some load-related issues that can be solved by adding more hardware. Not all of them, but some can. So let's look over an example. Now, this was in the dark ages before EC2 and auto-scaling. This was a service where we were running tens of thousands of machines, and we had to make sure we were scaled for peak. In the dark ages before EC2 and AWS and auto-scaling, we actually had to get this number right, month, 2 months in advance, because it took that long to provision thousands of machines to be ready for traffic. On a regular off-peak day, we had this cluster, let's say about 10,000 machines. We're running it at 50% CPU. This is to allow a little bit of room for unexpected traffic, or also to allow for ad hoc jobs that might have higher priority. So we're running with quite a bit of room here. And we're processing n number of transactions per second. And for peak traffic, we're expecting about 3 times that. So then we're thinking, we can't just triple the amount of hosts that we have. That's not cost effective, and that also is very, very difficult without AWS. So what we agreed to do is, for peak traffic, we're going to take our fleet to about 85% CPU. So then the math becomes not too bad. You say, right now we have 10,000 hosts, we have n transactions per second, we're running a fleet at 50% CPU. We are expecting 3x number of transactions per second. We have agreed to take the fleet to about 85% CPU. How many hosts do we need? And so we did this math and we provisioned the hardware. And me being the cynical engineer that I am, I didn't believe that was correct. And I had about 3 weeks to prove that. So in 3 weeks, I had to write a system that was going to simulate the load that the entire country and the entire world puts on Amazon.com on peak traffic. That's not a lot of time to write something that needs to be horizontally scalable and secure and reliable and so forth. But I did it with AWS, and I'll be talking a little bit about how we did that. And we started running the test, and surprise, surprise, we got thousands of machines in production running at pretty much 100% CPU. We stopped it right before we felt that our production system was compromised. But at this point, we were running a production service at 3 times the amount of traffic that it was expecting any other day. Turns out our math wasn't right. Why? Well, things scale linearly until they no longer scale linearly. And that's a thing that we're reminded of constantly at Amazon.com. At the scale that we run, things always start kind of breaking. Most of the things that you take for granted start breaking when you get to a certain scale. But we had done something very, very important, which is we took our system to its breaking point. We had extremely good data on how it scaled, according to how many machines we're adding and how do they handle the transactions coming in. And we're able to add additional hardware and rerun the test, and this time we actually peaked at 85% CPU. So this is a happy case. We run our test, we figure out how many machines we actually needed, and we happily lived ever after. Much, much simpler world today with AWS, with EC2 and auto-scaling. You don't actually need to do all this complicated math and start provisioning hosts way in advance and so forth. But at the time, we were moving our systems to AWS. Last year for reInvent, Laura Gritt did a great talk on moving the retail site to AWS. If you're interested, you can catch that on YouTube. Then there's some other load-related issues that can only be solved by redesigning your architecture. This is where we start getting more and more expensive. Let me give you another example from my Amazon life. We're running a system here that has an ingestion fleet on the left, and it is hooked up with actually EC2 and auto-scaling. Then, as it's ingesting the data, it's putting the data in S3. It's writing a little bit of metadata about the data in a database, and it's processing the data in Hadoop, a very, very big data MapReduce system. And then there's an output fleet that makes the data available to our users. So for the most part, the system is pretty scalable. We've got an ingestion fleet that will auto-scale. We've got S3, which as far as we're concerned, it's infinite. We've got Hadoop, which is basically designed for very, very big data. And we've got an output fleet that's also designed to auto-scale. This looked great, and we started doing load testing. And the first thing we saw was that, in fact, we didn't have the right number of hosts for the ingestion fleet. So the ingestion fleet starts running hot. CPU starts running at 85% or so. And when it gets to about 85, auto-scaling kicks in and provisions a whole bunch more hardware. At this point, we're high-fiving each other, saying, this is awesome. It is so much easier now with AWS and EC2 and auto-scaling. It just magically auto-scaled. But of course, there's a little bit more than that. So this database, which is not an AWS database, but a third-party provider of databases, wasn't properly scaled to handle that many more hosts hitting it. So database starts getting hot. Latency for writes start increasing, and some of the writes start failing and so forth. So we end up with all the hosts that we just auto-scaled. They're worthless. They're all just still refusing connections because they can't connect to the database underneath. Lesson learned here is that your system is only as scalable as your least scalable component. And in this case, we can move the database to bigger hardware, keep moving it to bigger hardware, but we could see the writing on the wall here. At Amazon scale, we were going to get to a point where we can't move it to bigger hardware. And in fact, we often get to this situation with a lot of our services. So I had to go back and redesign the system and put DynamoDB as one of the options here, and we lived happily ever after. But we had to redesign our system a little bit to actually take advantage of Amazon DB properly. Then there's some load-related issues that just cannot be solved by adding more hardware. This is when it gets really tricky. Third example for my Amazon life. We're testing a system that we're expecting it to max out in terms of CPU or maybe network bandwidth. We don't generally expect our systems to have problems with disk space. At Amazon, we believe disks and hosts are pretty ephemeral. They will die, so we don't necessarily take it for granted. Whatever you're writing to disk, you could lose at any minute, so we don't use a lot of disk. But we do monitor it when we're testing things. And we're load testing a system. It's using about 5% disk. And we start our load, and we see something very strange. Disk usage starts climbing up. It climbed from 5% to 20% in a matter of 5 hours. And looking at the traffic that we were about to put on this service, we were going to run out of disk space in a matter of about 10 hours. So by the time we actually got to peak traffic. And that left us scratching our heads a little bit. We thought, we can keep adding hardware to this problem. We can add another 1,000 machines, but they will all happily run out of disk space as well. No matter how many hosts we add, they'll just continue running out of disk space. And when they do, they'll start refusing connections. Turns out we had a bug in production. We actually had it for many, many months, probably about 6 months or so. The reason we never noticed is because the payloads we were getting during off-peak traffic, we were actually pretty small. The bug was a bug under which if the payload was bigger than a certain number of bytes, we would leak a file handle. That wasn't very common during off-peak traffic, and so once in a while we would leak a file handle, but eventually a developer would check in, we would redeploy, JVM would get restarted, file handles would get freed up. We never noticed. We actually had this bug in production for many, many months. But during peak traffic, we would have actually had thousands of machines refusing connections because they were 100% disk used. As we start thinking about doing load testing, there's actually 4 different terms that I've seen used almost interchangeably in the industry. And to me, they mean very, very different things. There's a lot of overlap between them, so you can actually be doing them all at the same time. But they do mean very, very different things. And to illustrate this, I use the treadmill analogy. So what's load testing? In the treadmill analogy example, you're expecting to run a marathon. For our systems, we expect a certain peak, maybe on Black Friday, maybe Cyber Monday, maybe Christmas Day when people open up those Kindles and power them up. There's some sort of peak that we're expecting. And we know what it will be like. At least we have forecasts that we expect this much traffic. And we want to make sure that we can handle that peak coming our way. In the treadmill analogy, you're going to run a marathon. You know it's 20 miles. You know it's 3 hours or whatever. You have a goal to reach. So what you do is you get on the treadmill and you run and run and run. You don't do the whole thing the first time. Maybe you run 5 miles. Make sure you can run 5. Tomorrow you run 6 miles. Next day you run 7 miles, et cetera, et cetera. So you are in this treadmill replicating, simulating what you're expecting to do in real life someday. So that when the time comes, you can cross that finish line with success. For us, doing proper load testing means the system, the retail side is up and running when you go 24/7. Black Friday, Cyber Monday, Christmas, you mention it. Stress testing, on the other hand, is a lot more evil than that because the purpose of stress testing is to break things. The purpose of load testing was to actually not break things. Happy outcome of doing load testing is system would work for a peak, we can go have a beer and be done with our day. Stress testing, on the other hand, is all about breaking your system, taking it to its breaking point. So in the treadmill analogy, we put you on the treadmill, and we just keep increasing the speed until you actually fall over. We want to see when do you fall over. That gives us valuable information on having mitigation plans for what do we do when this happens. Resilience testing, on the other hand, is all about horrible things happening to your system that you don't necessarily anticipate will ever happen, but they might. So in the treadmill analogy, what we do here is we break your leg and we put you on the treadmill, and we want to see that you can still run. Maybe you can't run at full speed, but you can kind of hop along the treadmill with your broken leg and actually do something. So this is all about things like data centers going down, hosts going down, your dependencies going down. It's all about really weird situations that you don't normally expect to see, but you might, right? Somebody took a picture of this half-naked guy running in the snow. Not something I would do, but it happened. And then performance testing is all about how does latency and throughput change as you're increasing your number of transactions per second or concurrent connections, or whatever it is that you consider load. But most importantly, how do we use AWS for doing all these things? Let's talk about generating load and different ways of generating load. You can have traffic that you have saved, and you can replay that traffic again to generate load. Or you can have some sort of artificial traffic that you're generating. You're generating an artificial rate. That can be transactions per second or concurrent connections, and an artificial blend of operations. These are actually pretty different problems, so let's start with the first one. How can we replay traffic from something that we've saved up? But before I do that, I want to introduce you to what I call the most useful design pattern for AWS ever. I use this thing for everything. It's very versatile. What does NASA do when they need to fix their problems in space? They use duct tape. It's actually true. I didn't believe it until I Googled it. Duct tape is one of those things that you can use for anything you want. I have it around the house. Baby's diaper breaks. You put duct tape around it, problem fixed. You can do anything you want with duct tape, right? You can do this. I've always wanted to do this to my kid. This is not my kid, because I don't want CPS to show up my doorstep, but I've always wanted to do it. So I admire this guy. You can do anything you want with duct tape. It's a very versatile thing. You can make a cat hat. You can make shoes. Pretty much anything you want, you can do it with duct tape. So to me, this design pattern is like duct tape of AWS. But first, let's look at how do we do this the hard way. So this is a pretty common computer science approach. Nothing wrong with it. It's been used for many, many services. Master-slave type design. So you've got a master that knows who its slaves are, and it tells the slaves to do work. There's nothing wrong with it, but it has a lot of complexity that it doesn't need to have. First of all, it's a very tightly coupled system. When you start using AWS, you start learning the value of decoupled systems. What you need here is the master has to know exactly what its slaves are. The slaves have to know exactly what their master is. There has to be this constant communication back and forth between them. This puts you, the master, in the business of health checks. You have to know the health of all your slaves at all times. Maybe these slaves have to do some sort of health, like ping back, or the master has to do some sort of health ping, or something like that. Either way, you have to get a state of the system, and your master has to know who's doing work, who's not, and so forth. Master dies. It's a single source of failure. It's a single point of failure. And the more hosts that you run, you'll realize that they die all the time. This will happen. Your master dies, your slaves don't know what to do. Likewise, let's say that what you're trying to do is you're trying to achieve 12,000 transactions per second. So master knows it has 4 slaves. It'll tell each slave to do 3,000. But then slaves die too. And so master has to know, a slave died, I have to redistribute the load, ask the guys who were doing 3,000 to now do 4,000. Well, this puts you in 2 different buckets that I don't ever want to be in. One, it puts you in the business of having to know the health of every single host that is using you. Health checks is one of those things that looks deceivingly simple. You look at this problem and you think it's not hard, right? Each host can send a pulse once in a while saying, I'm still alive. How difficult is that? Actually, it's pretty non-trivial. As you start looking into the edge cases, especially at a very, very high scale, it's a hard problem. I don't want to solve it. It's been solved by many people, and they've spent a lot of time solving it. It also puts you in the business of having to redistribute load. So it puts you in the business of having to load balance. And load balancing is also a very difficult problem. It looks incredibly easy on the outside, but the more that you start thinking about it, the more that you start thinking about edge cases, and the more that you start actually doing it at the scale that we do at Amazon, load balancing is a very hard problem. So those are two problems I don't ever want to solve or have to solve when I have to do something very, very quickly. Load balancing and health checks. That was the hard way. How do we do this the easy way? Not too different, actually. Instead of master-slave, we have a controller, a queue in the middle, and a bunch of workers. So controller is kind of like a master, and workers are kind of like slaves. But there's this magical thing in the middle, a queue. Why is this so much better? Well, first of all, you've decoupled your systems. Your controller doesn't care what workers are actually listening to the queue. Its job is to write to the queue. And as long as I'm the controller, as long as I'm putting a job in the queue, and it disappears from the queue, that means somebody's doing it. I don't care who. Host can die. Host can be brought in. Host can be resuscitated. It doesn't matter. As far as the controller is concerned, things are either getting done or not, and it knows based on the size of the queue. Likewise, the workers, they don't really care who wrote a message. They don't need to have this tightly coupled system where the workers have to know who the controller is. Their job is, once in a while, go to a queue. If there's a message waiting there, that's a job to be done. Grab it, go do it. I wish I could take credit for this. It's not my invention. It's not even a computer science invention. It's been around forever. What happens when you go to a restaurant? Waitress takes your order, writes it on a sticky, goes back to the kitchen, puts the sticky on some sort of order wheel. There's potentially many, many chefs inside, and whichever chef is free will go in there, grab the first sticky out of the order wheel, and go do it. This is the way people have done this for many, many years, hundreds of years. It's actually incredibly effective. You have all the information that you need to know about the health of your system in that order wheel. If you've got stickies growing and growing and growing, then you know you don't have enough chefs in the kitchen. You need to get on the phone and call and get more chefs to come work. If a waitress comes in and puts a sticky in there, there should be a chef available to pick it up and go do it right away. This is pretty much the same for distributed system. Controller puts the job in there. It wants it to get done right away. There's a worker available to pick it up and actually go do it. So this took us out of the load balancing business. Who's doing load balancing here? Nobody. The workers can grab a job whenever they're free and available to do it. If the controller puts a job, if nobody available, queue size will grow. Queue size tells you everything you need to know. Also takes you out of the health check business. You don't care who's actually listening to the queue. As long as I put things in and they disappear, and I'm good. I can add more workers when the queue size is growing. I can add more controllers and have them write to the same queue. So how do we use the design pattern to replay traffic to generate load? How do we do this in the 3 weeks that I had to write a system to simulate the load that the entire country and the entire world was putting onto the Amazon.com retail site? We started off with a test data repository. So this is an abstract concept where we have data to be replayed. And we have a controller, and the controller goes to the test data repository and says, give me a list of all the files that contain data to replay this 1 minute. This data repository has information on these are the files that I should be replaying this minute, gives me that list. And then as the controller, I put each one of these files as a message in my queue. Then I have a worker that is listening to that. So hopefully there's a free worker that is able to grab that message, go to the test data repository and download the file, and actually create the load process, take that data, that is basically serialized transactions, and deserialize them back into real transactions. So my design pattern seems pretty effective for this problem. Eventually the workers will grab the data, will hit the service under test. Things look good. And you're going to have potentially hundreds or maybe thousands of hosts doing this. So it's very important to know the health of the system. You want to get metrics and dashboards out of these hosts. If I'm creating a system that is putting load onto a production environment and can potentially jeopardize that production environment, I want to know what it's doing at all times, and I want to know how to stop it. So queue size tells me everything I need to know. If the queue size is growing, I don't have enough workers to put the load that I'm trying to put. The system looks good, but it would take an incredibly long amount of time to do it. I only had 3 weeks. How did I do it with AWS? Well, first of all, test repository was super easy to do. Basically, as we're getting production data that we want to save so that we can replay, save it to S3. You can encrypt it, you can secure it. It's a durable format. As far as I'm concerned, as an AWS user, it's a pretty infinite resource. I can keep putting data in, and it's pretty cost effective. It has a few other cool features, such as you can ask it to clean up your bucket if it matches certain criteria. So I could say, for the files in this bucket that I'm replaying, if the files are older than 30 days, clean them up. So at any given point, I only have 30 days of data that I can replay. Otherwise, this would be petabytes and petabytes of data. I need to index this data so I can find it later. And so I use DynamoDB for that. And so the test data repository is just a very thin layer that allows me to say, give me the files for this minute. Goes to DynamoDB, gets the list of files for this minute, and that's just metadata that we saved up in DynamoDB. And it puts them as messages in the queue. Amazon SQS, Simple Queue Service, is absolutely fantastic for doing queues. Gives me a couple of really cool things. One of them is the state of my system is now in the cloud. I don't have it on a host that could die right now. My controller, my workers could die any minute. But the entire state of the system, the things that need to happen, are in the cloud. They're in the queue. Also gives me resilience. So when you dequeue a job off SQS, you're actually not really deleting the message from the queue. You're turning its visibility flag to false. What that means is I've dequeued something. Nobody else can dequeue it for a certain number of time, for a certain number of minutes or seconds. And so worker gets a job, and it starts working on it, but it dies. After the visibility period timeout, that job comes back to the queue, and a different worker can grab it. So this gives me the resilience that if I have jobs on hosts that die, those jobs are not going to get done by that host, but eventually a different host will pick it up and will actually do it. This gives me the resilience without having to worry about who's alive, who's not, and what are they doing. CloudWatch is great for posting metrics and getting pretty charts out of it, so we use that for that purpose. EC2 and auto-scaling are absolutely fantastic for getting our hardware. Generally doing something like a replay, you have a very temporary need for hardware. You don't need to allocate thousands and thousands of machines for months at a time. I basically want to start, get a whole bunch of machines, start running my test. And additionally, I don't need to know how many machines I have, because with EC2 and auto-scaling, I can say, whenever I can start with a guess on how many machines I need, and whenever I start, if it reaches 80% CPU, start allocating more hosts. If it's under 30% CPU, start getting rid of some hosts. So the system can go up and down in terms of how many hosts it has without me having to do anything about it. Now, remember the dark ages, we had to figure out exactly how many hosts we need for something, get that provision, et cetera, et cetera. The system can just automatically go up and down as it needs to. And it can be even smarter than that, because the queue size I mentioned, it gives me everything I need to know about the state of the system. I can actually start auto-scaling based on the queue size. If the controller is putting jobs into the queue size is growing, then that means I don't have enough workers, so I can start allocating more and more hosts whenever I see that queue size growing up. And then as I allocate more hardware, that queue size is going to go down. That's all handy for replaying traffic from real world. But how do we do the second part of this, artificial rate? Why would you want to do that? Maybe you don't have real world production data that you want to replay. Maybe the traffic is not safe to replay. Maybe you're expecting changes in production that you don't have a way to have them today. These are things like controlling the rate, so the number of transactions per second, number of concurrent connections, controlling the blend of operations. Maybe your system is doing reads and writes and deletes, and you're expecting a change in that. And controlling the duration, how long you want to run it for. So let's say that you can define your load in terms of steps. First step, you want to run at 50,000 transactions per second for 20 minutes. And you've got a blend of operations, maybe 99% read, 1% write. You've got other steps, 85,000 TPS, and so you're changing the number of transactions per second, you're changing your blend, you're changing your duration. You can define the load in this way, number of steps and different steps. So how do we do 50,000 TPS, transactions per second, for 20 minutes with this particular blend? Use divide and conquer. And the problem of doing 50,000 TPS for 20 minutes is really the same as the problem of doing 50,000 TPS for 1 minute 20 times over. So we've taken our problem and we've broken it up into smaller chunks. Now our problem is doing 50,000 TPS for 1 minute. Use the same approach. It's the same as 5,000 problems of doing 10 TPS for 1 minute. What we did is just divide and conquer, take a big problem and break it up into smaller chunks, break it up into smaller chunks. What we now have is a very granular step. And granular steps are great for what? They're great for putting into queue. Each one of these little granular steps can now become a tiny little job that you put into the queue. So behold, we have the same design pattern that we use for replaying traffic that we can use for creating an artificial blend of load. Amazon EC2 Spot instances is a new hot thing. I've seen mentioned a lot in different talks in the past few days, and I will mention it also. It is a great way to inexpensively test. There's lots of teams out there using Spot for very, very cheap testing. This is because you can get EC2 instances for a lot cheaper than you get on demand. Maybe 90%, even up to 90%. You name your price, and if Amazon is able to match that price, you get the hardware. It needs to be interruption-tolerant tasks and time-flexible. So if your load testing can be interruption-tolerant and time-flexible, you can actually do this for very, very cheap. There's a couple of different approaches that I've seen people do. One of them is they can use Spot for achieving bursts of traffic. So they use on-demand instances to create the load that they're trying to create, just kind of like the expected load. But you want to see what happens when you have a burst of traffic. What happens if you're doing 10,000 transactions per second, but all of a sudden you have a burst of 100,000 TPS? Great. You can do that with Spot. You can do a bid for Spot, and whenever that price becomes the price that Amazon is able to match, then you get your host and you do this burst of traffic. There's other teams that are using it kind of as a first attempt. So when they start doing load testing, they try to get Spot instances. And if that fails, they'll go and try to get on demand. So worst case scenario, you're doing what you were doing before, you're just getting on demand. But best case scenario, you can actually get those hosts for much cheaper than you were getting them before. This allows you to do something that usually costs a lot of money for very, very cheap. Not sure what I just did. Takeaways for this. First, load and performance related issues can cost you a lot of money, reputation, customers. You don't necessarily get to add hardware to all the problems, and even if you could, you don't necessarily want to. But with proper load testing, you can identify the issues, and you can save yourself a lot of trouble by being ready for it. And you can do that with AWS very, very quickly. If we're able to do it for creating a system to simulate the load the entire country and the entire United States is putting onto Amazon.com retail site, it scaled for our needs, and it did in a way that was cost-effective and durable and secure, and all the other great things that come out of using AWS. So with that, I thank you for your time. Please fill in the feedback forms, and I'm happy to take questions.